Imagine you're on a rocket, flying through deep space. Your engines are running, and your rocket's accelerating faster and faster. What do you expect to happen when you switch your engines off? It turns out your rocket doesn't slow down, it simply stops accelerating. This is because we're in deep space, where gravitational fields from planets are negligible. In truth, there is no stars to be seen. Hence, there is no friction to slow the rocket down, so it simply keeps going at the same speed. What we've come across is the first half of Newton's first law. An object in motion stays in motion in the absence of external forces. In order to stop the rocket, you'll need to use the rocket's booster to slow the rocket down. Of course, once you've finally stopped the rocket, you won't be able to move it again unless you use the engine. That's the second half of Newton's first law. An object at rest stays at rest in the absence of external forces. To explore this a little further, let's come back down to Earth and look at what happens with a car. When the engine isn't running, the car stays at rest, just like the rocket. However, when it comes time to start moving, the engine isn't the only force that acts on the car. There's also friction. Increasing the force from the engine causes the force of the engine to be stronger than the friction pulling the car backwards, causing it to accelerate forwards. When the force from the engine is equal to the force of friction on the car, the forces are balanced, and the car acts like the rocket did when the thruster was shut off. It simply keeps moving at whatever speed it was moving at before. In fact, it's exactly the same thing, according to Newton's laws. Balanced forces will have no effect on an object at all. This should make sense. When the engine is shut off on Earth, however, the force of friction causes the car to decelerate until it eventually stops. Once again, now the car has stopped, the forces acting upon it are balanced. Indeed, when the car does eventually stop, the force of friction is also zero. It's important to be clear that force isn't the same thing as acceleration, though they are related. Force is more like a measure of effort. Acceleration does depend on the amount of effort being put into moving something, but also on how hard it is to move that thing. To illustrate this, we're going to compare the acceleration of one car and a car towing a second car. Both cars are able to produce the same amount of force. Clearly, the two cars are only able to accelerate half as fast as one car. This is simply because it's twice as difficult to move two cars as it is to move one car. This exposes the equation that makes Newton's second law, F equals ma, which we can rearrange as A equals F over m. This equation states that the acceleration an object experiences is equal to the effort being exerted on that object, its force, scaled to account for the mass of that object, which in this case measures how difficult the object is to accelerate. These first two laws are able to explain many phenomena we experience every day, but there is one more law we should be aware of. During our time on Earth, the car has also been experiencing the force of gravity, which is effectively pulling it into the ground. The question arises then, why isn't the car sinking into the ground? We know, from Newton's first law, that for an object to stay at rest, the forces acting upon it must be balanced. This means that there must be a force acting upwards, against gravity. It turns out that this force actually comes from the ground itself. Newton's third law states that for every action, there is an equal and opposite reaction. The force due to gravity of the car down on the ground is balanced by a force upwards from the ground on the car. To illustrate this another way, let's explore a specific type of friction, called air resistance. When a car accelerates through the air, it hits particles of air. The particles in turn push back on the car, acting against it, to slow the car down. The reason it becomes progressively more difficult for a car to accelerate is actually that the faster it goes, the more particles of air it hits, increasing the force acting to slow the car down. Another way to understand Newton's third law is exploring what happens if our car hits a heavy rock. The rock pushes back against the car, causing it to slow down, and forcing the car's engine to produce more force in order to maintain its speed. This also links with Newton's second law. Just as when the car was towing the other car, the increase in effort required to accelerate the car means that unless the amount of force also increases, the car will decelerate. Newton's third law allows us to extend our understanding about how objects move to how they interact with each other. Newton's laws are a relatively simple starting point that allows us to explore the most important ideas in physics. I hope this video helps clarify them, and there's more videos on these topics to come.